Welcome to Spaceverse, your portal to cosmic adventures. The James Webb Space Telescope has just delivered some truly astonishing images of ancient galaxies, ones that are much larger and brighter than we ever thought possible. These unexpected findings are upending our traditional understanding of dark matter and have sparked fresh interest in an alternative theory known as modified Newtonian dynamics. This theory offers a completely new take on how gravity works to shape galaxies. And in today's video, we're going to explore Webb's groundbreaking discoveries, compare them with the long-established dark matter theory, and dive into what these revelations could mean for the future of cosmology. So sit back, relax, and let's dive into this cosmic mystery. When the James Webb Space Telescope began its observations of the early universe, scientists expected to find small, faint galaxies, fragments from the very beginning of cosmic history. Instead, what Webb has uncovered is nothing short of mind-blowing. It has spotted massive, incredibly bright galaxies that are far larger and more developed than what current models predict. These galaxies don't just appear to be larger in size, they seem to have formed incredibly quickly, far faster than the traditional dark matter model would have suggested. Now, according to the widely accepted cold dark matter model, dark matter is an invisible substance that plays a crucial role in the formation of galaxies. It exerts a gravitational pull on gas and dust, gradually guiding them to form stars, planets, and eventually entire galaxies. This process occurs over billions of years, allowing galaxies to grow slowly and steadily through mergers and the accumulation of material. This model has been the cornerstone of cosmology for decades, helping us understand the size, shape, and distribution of galaxies across the universe. But here's where things get really interesting. Webb's findings seem to contradict this slow growth picture. Instead of finding galaxies that have evolved gradually over time, the massive and bright galaxies captured by Webb appear to have skipped the long build-up predicted by the dark matter model. These galaxies are fully developed, and in some cases, they've reached a size and brightness much earlier in the universe's timeline than what we expected. In fact, these galaxies seem to have formed at a rapid pace, in a way that the current dark matter theory can't fully explain. This is a huge deal because it calls into question whether the dark matter model is the whole story when it comes to galaxy formation. If these galaxies could grow so large and bright so quickly, it suggests that there might be something missing in our understanding of how galaxies come to be. Perhaps dark matter isn't the only factor at play, or maybe the theory itself needs to be adjusted. This is where the idea of modified Newtonian dynamics comes into play. ND offers a different way of understanding gravity, proposing that gravity behaves differently on cosmic scales, potentially allowing galaxies to form more rapidly than dark matter models suggest. So, what does this mean for the future of cosmology? Webb's discoveries are forcing us to rethink some of our fundamental assumptions about the universe and how it works. They open the door to new possibilities. Maybe our understanding of dark matter isn't complete, or maybe alternative theories like M&D will give us a better framework for understanding the forces that govern galaxy formation. Either way, this is an exciting time for astronomers and cosmologists, as these findings push the boundaries of what we know and offer new avenues for exploration. Modified Newtonian dynamics, or MND, presents an exciting twist on the traditional dark matter theory. Instead of relying on invisible matter to explain cosmic phenomena, M&D suggests that gravity itself might not always follow Newton's familiar laws, especially in regions with extremely weak gravitational pull, like the outer edges of galaxies. While Newton's laws have been essential for everything from understanding why apples fall to explaining planetary orbits, M&D proposes that in low acceleration environments, gravity behaves a bit differently. This theory was first developed to solve a puzzle known as the galaxy rotation curve problem. Observations showed that stars on the outer edges of galaxies were speeding around much faster than expected, based on just the visible matter alone. Traditionally, scientists have solved this by introducing dark matter, an invisible substance thought to surround galaxies, providing the extra gravitational force needed to explain those high speeds. However, M&D offers a fresh perspective. Rather than adding unseen matter, it suggests that the laws of gravity themselves change in these low gravity areas, providing the extra force needed to keep stars moving at such high speeds. M&D becomes especially intriguing in light of Webb's discoveries about the early universe. If gravity operates differently at the edges of galaxies, it could mean that galaxies form and evolve at a faster pace than the standard models predict. This could help explain why Webb is capturing images of massive, fully developed galaxies from the early universe, galaxies that dark matter theories would expect to be much smaller and less developed. Of course, MND isn't without its critics. While it does a great job explaining galaxy rotation curves, it doesn't seem to work as well for larger cosmic structures like galaxy clusters. Plus, it doesn't yet offer a comprehensive framework that can explain all the phenomena dark matter theories account for. Still, Webb's findings have some astronomers rethinking MND, especially since its predictions seem to align with the rapid galaxy formation observed. While it's unclear whether MND could replace dark matter theory entirely, its ability to explain certain cosmic puzzles keeps it a fascinating and relevant alternative in the world of cosmology. The discoveries made by the James Webb Space Telescope are truly groundbreaking, shaking up one of the foundational pillars of modern cosmology, the dark matter theory. Dark matter has been the go-to explanation for many cosmic phenomena that visible matter alone couldn't account for. It's been crucial in helping scientists explain everything from the formation of galaxies to the behavior of galaxy clusters and even the large-scale structure of the universe itself. However, if galaxies in the early universe can form rapidly without dark matter, it raises the possibility that dark matter might not be the all-encompassing answer we once thought it was. This leads us to an exciting new theory, tensor vector scalar gravity, which was developed by physicist Jacob Bekenstein in 2004. TeVeS builds on the ideas behind modified Newtonian dynamics while attempting to address some of its limitations. What's fascinating about TeVeS is that it introduces three new fields, tensor, vector, and scalar, to better describe how gravity works. These new fields are designed to align more closely with Einstein's general relativity. Essentially, TeVeS bridges the gap between MND and our broader understanding of gravity, offering an alternative explanation for galactic behavior without relying on dark matter. So how does TeVeS tie in with Webb's extraordinary findings? The theory suggests that gravity in these early massive galaxies might have worked differently than we expected, potentially allowing them to grow at a much faster rate than traditional dark matter models would predict. If TeVeS can explain this rapid galaxy formation, it could provide a fascinating alternative to dark matter. What's especially exciting about TeVeS is its attempt to offer a more complete theory, one that combines the successful predictions of MND while also fitting seamlessly into Einstein's framework of gravity. With Webb's revelations in mind, TeVeS could very well hold the key to solving some of the most puzzling mysteries in cosmology, offering a fresh perspective on the universe's most fundamental forces. These exciting discoveries highlight the need for even more research and observations to fully understand what's happening in the universe. With telescopes and observatories like the Rubin Observatory coming online soon, we'll have even more tools at our disposal to gather data on how galaxies form and behave throughout the cosmos. On top of that, the James Webb Space Telescope will continue its observations of distant galaxies, allowing scientists to dig deeper into whether these rapidly growing galaxies are more common than we initially thought. By studying these galaxies, researchers will be able to test the modified Newtonian dynamics, tensor vector scalar gravity, and the dark matter models in greater detail, ultimately helping us refine and improve our understanding of the universe. And that's it. Thank you so much for watching. We hope you enjoyed this deep dive into the incredible discoveries made by the James Webb Space Telescope and how they're reshaping our view of the cosmos. If you're as excited about these new findings as we are, don't forget to hit that subscribe button and stay tuned for more thrilling cosmic explorations.